Alright, now it's the time to talk about some concentration. Not the concentration like that thing you lose in class when I start talking too much. Instead, this concentration deals with solutions. So concentration is a measurement of how much stuff there is per area or per volume, and that's what we call concentration. So how concentrated a particular solution is. And when we think about area in terms of solutions, remember a solution is something that's dissolved in water, and so the area would be the amount of water that we have. So it's not the size of the container that it's in necessarily, rather it's how much water there is and how much stuff there is. So stuff would be the things that are dissolved. So in the case of these pictures down here, we see several different concentrations of red dye inside of water. Now, you notice how the beaker, it has a particular volume, so that looks like it's probably about a 600 milliliter beaker, which means up to the top is 600 milliliters. But the water, the volume is not all the way up to the top. So when we talk about the concentration of these solutions, the area won't be the full 600, it would just be up to whatever level this is. And so let's say it's 400 milliliters. So our area in this case would be 400 milliliters because that's how much water there is. That's how much solution there is. The stuff then would be the number of particles that are dissolved in there. So if we zoom in and look at a small little part of this solution right here, we can see that there's a lot of little dots. So those would be individual particles. Those would be the stuff. As we go down, you can see how it gets a little bit lighter. And that's because the volume is the same all the way across. So all of these are the same area, but they slowly have less and less stuff. So this one right here, it's only got 60 dye molecules as opposed to 120 here. And so that makes it less concentrated. Area stays the same in all of these, but the stuff changes, and so therefore the concentration changes. The numbers up top, those are the measures of concentration that we're going to talk about. That is molarity. So this first one is a 2 molar solution, then a 1 molar, and 0.5 molar, and 0.25. So you can see as the stuff gets less, the concentration also gets less, and you can see it in those pictures. So things like salt water, you can't look at salt water and see how concentrated it is. You can maybe taste it, and if it tastes saltier, that's more concentrated, and something that's only slightly salty. But you can't always see concentration necessarily. In the case of dye molecules, you can because they're visible. So if we have a particular solution inside of a container, that means we'd have a certain amount of water, and we'd have a certain amount of stuff dissolved inside there, and that would create a particular concentration. Now, how can we change the concentration? So we can either increase the concentration, and an increase in the concentration, if you increase it, that's called making it more concentrated. Sorry, that's crammed in there. But concentrated would be if you were to increase the concentration. If you decrease the concentration, so decrease the amount of stuff per area, that is called dilution. So we're making it more diluted. So we increase concentration, it becomes more concentrated. We decrease concentration, it becomes more diluted. Now let's remember what concentration really is. And it's the amount of stuff, the dissolved stuff, per water. In order to change the concentration, we can only change one of those. So if I wanted to make it more concentrated, if I wanted to increase the amount of stuff per water, I could add more stuff in there. I couldn't at the same time add more water because then the ratio would stay the same. So I could only change one thing. If I wanted to make it more diluted, so if I wanted to decrease the concentration, I could take away some of the stuff, so decrease the amount of stuff per water, but at the same time I couldn't also take out water because then the ratio would still stay the same. Another way that I could change the concentration is if I were to add more water. So if I poured more water into this, that would be diluting the solution. And all of those little molecules, they would spread out a little bit more and they would mix in throughout here. And so we'd be increasing the water, but we wouldn't be increasing the amount of stuff. And so that's going to create a more diluted solution. I could create a more concentrated solution by getting rid of some of the water, but the trick with that one is if I get rid of some of the water, I can't also get rid of stuff. So I'd have to boil it off or evaporate it. If I were to just pour it out, I'd be pouring out stuff and water, which wouldn't make a difference to the concentration. Okay, here's a picture that shows kind of that last concept. If I had a 2 molar solution of this red dye molecule, so 120 dye molecules inside of 1 liter. That would make it 2 molar. If I were to take some of that and pour it over into another beaker, okay, and if I transferred 250 milliliters, that would not change the concentration of the solution. Because 250 milliliters, that's a quarter of the solution, so I'm just pulling out a quarter of this, and that's decreasing both the volume and the amount of stuff at the same amount. So now I have 250 milliliters with 30 dye molecules, and that means the same concentration. It's still 2 molar. This would be like if you have a jug of purple-flavored Kool-Aid. That purple-flavored Kool-Aid, it has a particular taste, and that's because it has a particular concentration. Concentration is what makes it taste the way we want it to. If we were to dilute it or concentrate it some more, it would change the flavor, and we probably wouldn't like it as much. Now, if you were to take some of that purple Kool-Aid and pour it into a glass, that would decrease the volume of your pitcher, and it would put a small amount of it over here. Does that change the concentration? Does the purple Kool-Aid from the jug taste any different than the purple Kool-Aid in the glass? The answer is no, it doesn't, because the concentration doesn't change. The volume changes, but so does the amount of stuff. We're pouring out a small amount of volume and a small amount of stuff. And so the ratio stays the same. And concentration is all about the ratio of things to volume, or stuff to water. And since when we pour that Kool-Aid over, we're not changing the amount of stuff per water, we're not changing the concentration, we're not changing the flavor. And ladies and gentlemen, here it is, the ratio calculation that you need to know. So molarity is the ratio of moles of solute to liters of solution. So remember, solute is the stuff that's dissolved, and liters of solution, that would be your solvent, so the total volume that it makes up. So molarity, which we symbolize with a capital M, and it's imperative that you use a capital M, not a lowercase m, is moles of solute divided by liters of solution. So this would be what's dissolved this would be the amount in liters. So liters is important. It can't be in milliliters, can't be in kiloliters, anything like that. So let's look back at our old friend King Henry died drinking chocolate milk. And I'll give you a hint, most of the time our readings are going to be in milliliters, because that's what we measure in. When was the last time you measured something in liters? And so if we have something that's like, let's say 250 milliliters, in order for it to work in this equation, that needs to be in liters. So we're going to need to convert that over, which means we're starting right here on milliliters. We'd go over 1, 2, 3 places to the left, and that's going to get us liters. So that means we take our decimal on 250, go 1, 2, 3 places to the left. So 250 milliliters is the same thing as 0.250 liters. You got to make that conversion a lot during this unit, so just remember 3 places to the left, and you're in liters. Also important is that you're in moles when you do this calculation. So when we measure things out, like if I tell you to make a particular molarity of salt water, when you measure out your salt, you're going to be measuring it in grams, which means you're going to have to convert grams into moles. And that's just our old friend stoichiometry, where you divide it by the molar mass from the periodic table, and that will give you the number of moles. So make sure your units are in moles and in liters, nothing else. So here's a little thing that'll make your lives a lot simpler. So we're going to assume always, and this is true for pure water, so pure water, 1 milliliter of it would equal 1 gram. So what that means is if you take a graduated cylinder and you measure out exactly 1 milliliter of water and then put it on a scale, it's going to read 1 gram. So the density of pure water is so much that it's 1 gram for every 1 milliliter. And if you fill a graduated cylinder all the way up to 1,000 milliliters, which is the same thing as 1 liter, it's going to read on that scale 1,000 grams. So 1 liter, 1,000 grams, 1 milliliter, 1 gram. And we can assume this for all solutions then as well. So if you have a solution of, let's say, 100,000 milliliters, and we'll say it's, silver nitrate. We're going to assume then that silver nitrate solution is going to have the same density of water, which means it would weigh 1,000 grams as well. So that's not really true. A solution of silver nitrate, because of that stuff that's in the water, it's going to increase the mass by a slight amount. But to ease our calculations, and because the slight amount of stuff that's in there isn't going to affect it that much, let's assume that all solutions would have 1 gram for every 1 milliliter. And, this is really simple, because then if you have 500 milliliters, that's going to weigh 500 grams. So it's a pretty easy calculation. Just convert milliliters into grams. Now it's time for some practice. So what is the concentration? And concentration is molarity. So what is the molarity of a 0.2 moles of sodium chloride dissolved in 117 milliliters of water? So molarity, we've already said, is moles divided by liters. So in the case of this question right here, we're given the moles. We know we have 0.20 moles of sodium chloride, and the volume is 117 milliliters. So remember, we can't leave it in milliliters. We need to put it into liters. So that means we take that decimal, move it over 3 places to the left, and it becomes 0.117 liters. And that number then goes up into our equation. And if we solve that out, so 0.2 divided by 0.117, that equals, with sig figs, 1.7. And the units on that, since before it was moles divided by liters, and moles divided by liters is the same thing as saying capital M, which is molarity. So the answer would be 1.7 capital M. We would say that as 1.7 molar solution of sodium chloride. Alright, here is a slightly different calculation. It's still asking us for molarity, and molarity is still the same thing. It's moles divided by liters. But now in this case, we're said we have 24 grams of sodium hydroxide in 300 milliliters of water, and we need to figure out the concentration. Well, molarity deals with moles, and we're given grams. It deals with liters, and we're given milliliters. So that means we've got to do a couple different calculations, a couple different conversions before we can finish this one. So let's start off by taking that 24 grams of sodium hydroxide. We need to get that into moles. How do we get that into moles? If you said a conversion factor, you would be absolutely correct. And where do we get that conversion factor? We get it from the periodic table. So 1 sodium, 1 oxygen, 1 hydrogen adds up to be 40 grams for every 1 mole. Grams cancels out grams, and we can find that to be 0.600 with sig figs, moles of sodium hydroxide. So there we go. We now have a number that we can use in our equation. So there is our number of moles that goes on top. The volume is 300 milliliters. Milliliters is no good to us. We need to convert that over to liters. So we're going to move that decimal over, get 0.300 liters, and we are now ready to solve. So we've converted grams into moles, 0.600 moles, and we divide that by the volume of water, volume of the solution, which is 0.300 liters. 0.6 divided by 0.3 is 2.00 for sig figs, and the units on that, everybody say it now, that's right, molarity. So what this means is if we take 24 grams of sodium hydroxide, dissolve it in exactly 300 milliliters of water, our resulting solution that we have just created would be a 2 molar solution of sodium hydroxide, which we could then use in a lab and an acid-base reaction, all kinds of different things. And of course I saved the best for last. So this question, how many moles of potassium bromide are there in 70 milliliters of a 3 molar potassium bromide solution? The next question is, how many grams are there? So with this question, we're saying that there is 70 milliliters of this 3 molar potassium bromide solution. So that means there's 3 moles of bromide for every 1 liter. And the questions ask is, how many moles, so how much stuff, how many particles is there dissolved inside of that solution? Remember that the equation is molarity equals moles divided by liters. In this case, we're not given the moles and the liters. Instead, we're given the molarity and the volume and the liters, and we need to solve for moles. So we need to find out how many moles there is dissolved in this solution. So let's take our numbers and plug them in. .070 would be our volume in liters. So molarity is going to be equal to our moles divided by 0.070 liters. And our concentration is 3.0 molar. And we're going to solve for moles right here. So we're going to do that by multiplying both sides by 0.70. That's going to cancel them out on that side. We need to multiply it by 0.70 on this side as well. So we rearrange this fun little equation. We solve it for moles, and we find out that there is 0.21 moles of KBr in 70 milliliters of this solution. So that's how many moles there is inside of this beaker right here. Next part of this question asks us how many grams is that. So let's say we were to take this and put this underneath a Bunsen burner, and we were to boil off all of this water. So there is nothing but potassium bromide in there. So we were to take away all of that liquid. How many grams would be left? This is a puzzling question I have proposed. But it's a simple calculation. We have 0.21 moles of potassium bromide. And we know that potassium bromide has a certain number of grams for every 1 mole. So how many grams is there per mole for potassium bromide? We add it up on our periodic table, and we see that there is 119 grams for every 1 mole for potassium bromide. So we just multiply 0.21 times 119. And we find out that with sig figs, there would be 25 grams of potassium bromide inside of that solution. We could take this backwards then. If we wanted to make a 3 molar solution, 70 milliliters of a 3 molar solution potassium bromide, we would dissolve 25 grams of potassium bromide in 0.070 liters, which is 70 milliliters, and that would give us the solution. If we boil it down, make that solution, boil it down, we would end up with, hopefully, 25 grams of potassium bromide. So there you go. That's concentration and how we do calculations with it. The thing to remember is just that the concentration is always molarity equals moles divided by liters. The overarching goal is always to find either moles, liters, or molarity. The units need to be moles or liters. If they're not, it's a pretty simple conversion, things that we've already done before. So as long as your units are right, you put the right thing in the right place, it should be a fairly simple calculation.